Okay, thank you. Kondo-san gave an overview of some of the more of a broad survey type of research we're doing to cover all the spectrum so that we will not have missed anything. But we're running several projects, in fact, Kengo-san's project, Kondo-san's project, and also he's involved in my project, which has a much more focused, try to get more focused view on innovating towards the next generation of a machine. This is still basic research. Don't get me wrong. This is not to say Fugaku-Next will be built this way or built by us and so forth. But this is a basic research, but I think to just give you some hope and also to kind of relieve you of some of the misconceptions we have about the next generation systems. Okay, and 100X is comparable to, let's say, mainstream, certain US vendors, processors, since H2FX is 3 times faster on HPC workloads, our goal is to achieve 33x over H2FX. Okay, so it's but again, this is a basic project. So our goal is to really look at something towards 2028 timeframe. And sort of entering the post-Moore era, we're already kind of start to slowly migrate towards that. We're seeing the limits of transistor increase with the lithography improvements plateauing. And the key is to see what can be done. And in the 2030s, this will definitely be true. And in the 2020s, we'll still have some advances, but so we anticipate by the end of the decade, we'll be hitting this, really this limitation will start to manifest seriously. And our next generation systems of the time will suffer from this. However, if we have a tangible solution, we can continue on to the 2030s and the decade, 2030s decade. So we're looking at, Kondo-san just showed this and a very grim picture, and with a general purpose processor, we can't really hope to achieve any goals like even be 33x faster compared to H2FX, or let alone 100x faster compared to traditional machines. You might argue that for accelerate like GPUs, you might be achieving 33x if we double the power, but the applications that Kondo-san presented was sort of a little bit skewed. There were some reasons why there were so many astrophysics applications, and although they don't occupy much of the system, they're very heavily compute intensive. But for normal workloads, that's not the case. Even for things like molecular dynamics, you might think is compute intensive, but actually the one that's categorized as compute intensive is a software called Modulus, which uses basically fast multiple method, which is compute intensive. But for normal workloads, you use FFT for PME, and the results from a mainstream use of molecular dynamics from things like what we created with Sugita-san's Genesis, and also things like GROMACS, we see that 1/3 of the time is being occupied by PME. So so if you zero out the particle interaction part, you only get 30% speed up. Okay, so in fact we did a sweeping analysis of many of the applications from not just from us but from DOE, suite of applications from DOE and other benchmarks, and we find that the majority of the applications are on the left-hand side of the roofline curve. Okay, so Kondo-san really has to adjust the benchmarks to make it more realistic, and to follow this pattern instead of what we did 10 years ago. That was taken 10 years ago. So anyhow, so achieving significant speed up given this situation, it really tells us that we need to increase the system bandwidth significantly in some way. And if you remember the slide shown by Kondo-san, although we get significant increase in the flops in the GPU system, the actual bandwidth of the system is not so different from the CPU-based systems, and the increase from Fugaku, which has 163 petabytes per second of bandwidth, is only a factor of 4 to 5. So for majority applications on the left-hand side, we can expect no matter what processor we use, if we maintain that level, we can only expect 4 to 5 times speed up over the existing systems like Fugaku instead of over 30. So what do we do about that? What we're doing is to kind of think of acceleration in a very different way compared to what people have been doing. Firstly, we envision a system like this. We have a general purpose many-core CPU, but greatly enhanced to accommodate much higher bandwidth by some ease, not just attaching HBMs, which Fugaku innovated for general purpose CPU, but we need to have much more aggressive technology to increase the bandwidth for many-core CPUs. But we also see possibility in acceleration, and probably we see the most promising one being sort of CGRA type of architecture. Well, GPU architecture may be extended also to accommodate that, so we'll also be looking at that. But CGRA, just one of the reasons why the Samanova, Cerebras, so on, has such high performance, not just because they have high compute capability, but also they have very high bandwidth afforded by the internal connections being connecting the execution units directly rather than going through registers or through memory. So the big deal is what kind of execution units should CGRA have, and how do they interplay with general many-core CPUs? Can they be subsumed into many-core CPUs? And the other thing that's not been, although it's been studied for 30 years, that has really not been made into mainstream in HPC, is near memory processing, because obviously that's a fantastic opportunity to save memory bandwidth. And there have been some work to do this in software, like one that's been done in China. But have a hardware support to do near memory processing would actually allow us to significantly increase our capabilities in terms of bandwidth saving, which of course in terms increases the application throughput for majority for the bandwidth bound applications, which are the dominant applications we're seeing. We envision, we have a strawman, we're trying to define some strawman architecture based on, let's say, Skylake, what would be possible using what would be the most state-of-the-art technology that would be available around 2028, combining all these elements. And also, we are studying each of the components in detail. So we're trying to have established ways where we can have a very accurate modeling of the system. And it's surprising that after so many years, we still lack the tools to emulate and to predict performance for these aggressive systems. We're also looking at the CGRA, what the capabilities, what they're capable of, or what they're not capable of. What are the trade-offs? Can they be incorporated into general purpose architectures and so forth, or can be the opposite and so forth. We're also looking at the memory architecture and the system software to support that, how to profile memory behavior, how to basically try to come up with algorithms and how to support algorithms that are largely memory bound, and of course near memory computing. Which has some innovative features. Unfortunately, due to patent and other reasons, I cannot introduce to you today. So just highlight a few things. This is our most recent paper done by a group of people, which is my Skunkworks team at RIKEN. And so the question is, so there's a lot of hype around matrix engines for HPC. So our task was to basically investigate whether they'll be useful for HPC workloads. Can it be a viable accelerator? So, of course, if you believe in various commercials, you might think so. But so we looked at existing platforms and what they're capable of, what their compute capabilities are, and also tried to extrapolate what would happen when we had different types of workloads. And in fact, although you think it's powerful. One anecdotal evidence that they're not performing very well, even in AI workloads. So like you might believe in AI workloads, matrix engines are giving you significant speed up. If you look at the HPL AI results on Fugaku and also on other machines out there using GPUs with matrix engines, yes, of course, they get great results. But if you look at the efficiency of HPL AI, which is mostly dominated by, which is a proxy for the convolutional kernel of convolutional CNNs, which occupies, so 80% of compute of CNN is about matrix multiply in low precision. If you look at that, A2FX achieves, it's just vectors, long vectors, achieves 93% efficiency, which is even better than the LIMPAC efficiency. So machines like Summit with GPUs, yes, they achieve fairly comparable efficiency to A2FX in terms of P64 LIMPAC, which is of course dominated by matrix multiply. Not as much, but right up there. But if you look at the HPLI, which is mixed precision, so it's FP16, and they of course these use the FP16 matrix engines in these systems. They only achieve 16% or even 10% of the peak. So the per chip performance is something around 20 teraflops or 30 teraflops instead of being hundreds of teraflops. And again, this is a proxy for CNN. And so this is sort of in line with the performance you would see if we just had vector FP16, not matrix engine. And on the right-hand side, right-hand side, on some of the AI workloads, you see some speed up like BERT or attention layer basically exhibits almost 3 times speed up by using matrix engines, that is tensor cores and NVIDIA terminology. But and some like LSTM, surprisingly, but so for something like ResNet 50, which is CNN, you only see factor 2. So it's still very up in the air. This is FP16 to FP32 to FP16 matrix engine. So we're seeing consistency here to the HPL AI results. So it's not 100% assurance, even for AI workloads, that these matrix engines are effective. And moreover, if you look at real applications, what we did was to basically detect any sort of patterns that we have level 3 BLAS in them. It's just a very hard work done by Jens Duncan and many others on my team. But we find a very small number of applications in portfolio have any sort of GEMM components, or either calling a library or even programming it by themselves. And that's why I said the white paper stuff is skewed, because it occupy too much GEMM and compared to reality. So, and if we extrapolate this to real data center or the supercomputing center workloads, we only see, even if we have perfect speed up by infinite speed up of the matrix engines, on the K computer, we only see 10% increase in improvements in terms of overall throughput. And even for Argonne, and this is for future system in Argonne, when we anticipate much higher workload and occupancy by machine learning. This is hypothetical, but only see 23% speed up. So all the silicon used for matrix engines will not be very beneficial in our conclusion. And so we have to, and that's largely due to the fact that we have, many of these applications are bandwidth dominated. And so CGRA, we're looking at as one way, because CGRA is very attractive in terms of being able to absorb bandwidth. And that's, again, one of the reasons why things like Samanova and Cerebras, they're not just deep learning substrates, they are data flow engines. And so we're doing various things like building emulators, design emulators, and also trying to do various types of performance assessments as to see how effective they are. And maybe they are, maybe they're not, but there is very good, promising. It's very promising to think that this may actually be one of the good solutions to accelerate applications with high bandwidth requirements. And also, the work is being done on development of memory performance, estimation tool chain, and also various ways to detect the access patterns of many core systems, because there's so many cores in a system. Very complex memory hierarchy is no longer trivial, how the memory is accessed. We need tools to detect that and optimize the applications as such. And of course, we need to have real algorithms in order to be able to exploit, because this may require some algorithmic change, because it will not be trivial just to take the existing applications, bandwidth-rich applications, and just put them on a new chip and expect it to perform. We may need to have some modifications in the algorithm to best exploit the capabilities of these new architectures to provide bandwidth to the applications, but in a non-trivial fashion. So with that, I'd like to add, and I would say, future is bright, but it's not what a lot of people may think. Okay, thank you.